Bismillahirrahmanirrahim. Dear students, today we are going to discuss on law conservation of mass and energy. First of all, what is a law? A physical phenomena, a physical process, a physical change or a chemical change. If the experiment is carried out on that phenomena, they are generalized. Number of experiments are carried on that, repeated experiments carried out on that, and they are put in the form of a generalization, a conclusion. That conclusion we call as law, a physical law. After that, now this conservation term, in any physical phenomena, in any interaction, in any process, in any change, if any measurable quantity, if any measurable property, that means a physical quantity, throughout that process, throughout that interaction, that remains constant, its value not changes throughout the whole process, then we can say that physical quantity is conserved within that process, and that law we call as law of conservation. We have law of conservation of mass, law of conservation of energy, law of conservation of momentum. Similarly, we have law of conservation of electric charge. So we will discuss these laws. First of all, today we will discuss on law of conservation of mass and energy. According to this law, mass in a chemical change or in a physical change, that remains constant. That means mass of the reactants in a physical change or in a chemical change, that is equal to mass of the products of that change. This law were given by a great scientist. His name is Antoine Lavoisier. Lavoisier in 1789. This is about Antoine Lavoisier's law, that is about conservation of mass. After that, we will add within this mass conservation law, we will add also energy, that were added later on. First of all, again during a chemical or during a physical change, mass of the reactants is equal to mass of products. So first of all, I will take any physical change. After that, any chemical change. Number first, I will say here, if we have a piece of ice, means H2O in solid form, if first of all we will weigh this, we will measure its mass. After that, heat up this gently, it will be converted into liquid water. Now after that, we will also weigh this one, we will measure its mass. From this measurement, we can say mass of this solid ice piece, that is equal to mass of liquid water. Simply within this change, this one being a physical change, within this change, mass of reactants is equal to mass of products. Now let us take this daily life example. For example, we have wood. We can burn this wood. Burn this wood, it is converted into ashes. First of all, this one plus this wood. After that, gases are formed. Gases are formed. If we will take the masses of these ashes, this soot and gases within this, then that mass is equal to mass of wood. So within this change also, mass of reactants, that is equal to mass of products. From these experiments, we can say matter is indestructible. Means matter can neither be created nor destroyed. So in an alternative way, we can state law of conservation of mass in this way: matter can neither be created nor destroyed. In a process, that process, if carried, is like in an isolated system, or we may say in an isolated system, the total mass before any physical or chemical change, that is equal to total mass after the change. Means after physical change or chemical change, or in simple words, the total mass of an isolated system, that remains constant. Or we may say, we can take the best example of isolated system, that is universe. We can say in universe, total mass remains constant. and this law we call as law of conservation of mass. Now let us take a chemical reaction between these two substances. For example, we have NaCl. If NaCl is added to silver nitrate, then a precipitate is formed, that is AgCl. After that, this one sodium nitrate. This is the reaction. If now we measure the masses of reactants and after that measure the masses of products, then we can say that we can conclude this mass is equal to this mass. So in any chemical reaction, sum of the masses of products that is equal to sum of the masses of reactants, means mass of these products that is equal to mass of these reactants. There are many number of chemical reactions in all chemical reactions except in case of nuclear reactions we can say mass of reactants is equal to mass of products. Let us take this example, decomposition of this mercuric oxide. When this is heated up, it is decomposed into mercury. After that, oxygen is released. First of all, balancing this reaction. Now, if we will take it as 100 gram, then here 92 this one 6 of this mercury will be formed, liquid mercury. After that, this one 7.4 gram of oxygen gas they will be released. Now their sum 92.6 plus 7.4, that is again equal to 100 gram. So within this reaction, mass of reactants that is equal to mass of products. So we can conclude in any chemical reaction, mass of reactants that is equal to mass of products. We will take clear reaction. For example, this one I will take here. We have this uranium, isotope of uranium having atomic number 92. This one has mass number. If bombarded by a neutron, here I will write this one as neutron. It is first of all converted into this isotope 92 or 236. This one being unstable, it now superlates into lighter nuclei. That reaction we call as nuclear fission. Within this nuclear fission reaction, these two nuclei are formed. Barium plus krypton. We know atomic number of barium, that is 56. Atomic number of krypton, that is 36. I will write here their mass numbers 141 and it is mass number as 92. After that, these neutrons they are released within this reaction. 3 neutrons per reaction. Within this reaction, if we will measure the mass of reactants and mass of products, it has been found sum of the masses of reactants. Sum of the masses of reactants means sum of mass of reactants that is always greater than sum of masses of products. Now, where is the remaining mass? That mass is lost and that lost mass is converted into energy by an equation given by Albert Einstein. We know this famous equation is equal to mc square given by Albert Einstein in 1905. So according to him, energy and mass, means mass and energy, they are interconvertible. He quoted this term, energy can neither be created nor destroyed. We will take an example by means of which we will be able to determine how mass is converted into energy. First of all, taking this mass 1 AMU. Now what is 1 AMU? We know it is equal to 1 by 12th of 1 by 12th of mass of one atom of carbon. Mass of one atom of carbon. This carbon 12 means this isotope. Now first of all, taking the values 1 by 12, after that mass of one atom of carbon that can be calculated in this way. We know mass of 1 mole of carbon that is equal to 12 gram. 12 gram per mole, molar mass of carbon. After that, we know within 1 mole there are Avogadro number of carbon atoms. Now taking its value, which is equal to 1 by 12. After that, I will write here this one, 12 gram per mole. Then number of atoms per mole, they are equal to, Na is equal to 6.022 into 10 raised to power 23. This one. Now 12 and 12, they cancel it with each other. After that, there is 1 by this term, 6.022 into 10 raised to power 23. This one means this is the number of atoms per mole. So this one and this one cancel it. Here remains this mass in grams. So this one being in grams, if converted into kg, that is now equal to 1.66 into 10 raised to power minus 27 kg. So this is 1 AMU of mass. Now if this 1 AMU is converted into energy, that according to Einstein, that is equal to E is equal to mc square. So taking the values here, m means 1 AMU mass, that is 1.66 into 10 raised to power minus 27 kg. After that, we know value of C, that I will take this one, 2.998, or you may write 3 into 10 raised to power 8 meter per second. This one, meter per second. Now this is square, so taking here square, multiplying these two terms first of all, it will be equal to 1.492 into 10 raised to power minus 10 joule. Now here I will take the units again. This one in kg. After that, this kg into this one meter square. After that, this one per second square. That is equal to joule. So this is the amount of energy in joule if 1 AMU of mass is converted into energy. Now we will convert this into million electron volts. We know this one, 1 electron volt is equal to 1.602 into 10 raised to power minus 19 joule. So converting this one into electron volt, this will be now equal to 1.492 into 10 raised to power minus 10 joule. Now we know this 1.602 into 10 raised to power minus 19 joule is present in 1 electron volt. That means 1 electron volt of energy is equal to this amount of energy in joule. So taking now this in million electron volt, we know 1 million means 10 raised to power 6. Now this is equal to 1.492 into 10 raised to power minus 10 joule. After that, divided by this term, 1.602 into 10 raised to power minus 13, means 10 raised to power minus 19 into 10 raised to power 6, that is equal to 10 raised to power minus 13 joule per million electron volt. I can write that in this way, million electron volt. After that, carrying out this division, that is nearly equal to 931.5 million electron volt. So we will remember this relationship. If 1 AMU of mass is converted into energy, the energy conversion is equal to 931.5 million electron volts. Now let us take this example. For example, if the masses are given in any nuclear reaction, we can convert that mass into energy. Now taking again this example, this one uranium-92, here 236, this is converted into barium and krypton. These neutrons, they are released, say this one, 3 neutrons, here neutron, I have written here number 3. After that, here its atomic number is 36, its atomic number is 56, this number is equal to 141, and this number is equal to 92. Again, I will repeat here, the mass of this nucleus is always within this reaction greater than the sum of masses of this nucleus plus masses of 3 neutrons. So there is mass lost, some amount of mass is lost. That lost mass is converted into energy, and that lost mass we call as mass defect. I will write here mass defect, this term. Mass defect within this reaction denoted by this term delta M, that is simply equal to sum of the masses of reactants. These reactants I have written here minus sum of the masses of product. Now, knowing the mass of this nucleus, after that masses of these nuclei, even mass of neutron, we can calculate this mass defect. We have the mass defect that is equal to 0.213. We know this one. 1 AMU gives us energy equal to 93.15 million electron volts. So mass obtained from this one, 0.213 AMU, that is equal to this product, 0.213 into 931.5. This product gives us the energy in million electron volts. So within this reaction, the mass defect, which is equal to this, that is converted into energy in million electron volts, equal to this.